This is lecture 4, the third part. This is going to be a lot of repeated slides at the beginning. I'm going to fly through it pretty fast. So instructions in general, they either do something or they tell you to go somewhere else and to do something. So what we're interested in is program flow control, and that is the way the program jumps around. So, you need to go somewhere else to do something where you have like case or if then else statements or particularly subroutines. So we have two types of jumps. We'll say we got unconditional jumps and conditional jumps. So essentially, if the program flow control goes somewhere conditionally, that's going to be a branch. If it goes somewhere unconditionally, that's going to be a jump. So we're going to stick to that vernacular here. And essentially, to be able to do these in hardware, what we're going to be doing is loading values into a register, which we call the program counter, or PC for short. So it's typically it's typically a counter, but on the RISC-V it's going to be a register. So you should implement it as a register. So I'm always loading something. Either I'm loading a new address, or I'm loading the current address plus 4. The memory is byte addressable. The instructions are 4 bytes long. To go to the next instruction, which is normal operation here, I'm going to add 4 to it and load it into the register. So essentially, this is my program counter here. This is essentially a register. This is the these 4 pieces of data I'm loading into it. So I'm either loading the current PC plus 4, or I have 2 jumps here and 1 branch. I'm loading one of those things into the counter, to the program counter, which is a register, and that's going to allow me to jump around. So this was the first program we looked at. This is the idea here. What's important here, it has a jump instruction, which is an unconditional branch. So when it hits this instruction, it is going to jump to main. Main is a label, essentially a label associated with this instruction. Main is actually a number. It's actually the address in program memory of this instruction. And the assembler takes care of that for you. We don't have to deal with numbers directly, but we kind of have to deal with it indirectly. So once again, unconditional branch with to main here. It jumps backwards, and more to say on that later. This is our second program. So the program flow is going to hit that instruction, and then it's going to hit this instruction. This is a conditional jump, we'll say, or a branch instruction. So essentially the condition associated with it, if that condition is met, then it branches, it takes the jump. Otherwise, it drops down to the next instruction. So this happens to be a BEQ. If the 2 values in these registers are equivalent, it jumps to the instruction at that address, which is down here. Otherwise, if they're not equivalent, this condition fails, it goes on to the next instruction, etc., etc. You can see there's actually 2 conditional jumps in here. So these are the unconditional branches or jumps here. These are the official pseudo instructions. Like I said, I never used those. I use jump. I use this J. It works perfectly. I've implemented these instructions, but I actually don't use them in the code. The only jump instruction I use in the code is J, so I'll leave it at that. I don't think you'll need to use anything besides that. Branches, there's a whole bunch of branch instructions. There's 6 pseudo instructions and about 10 other, there's 6 base instructions. I said that last time too. There's 6 base jump instructions, branch instructions, and there's about 10 branch pseudo instructions. Okay, so if the condition is met associated with the branch, it takes the branch, otherwise it drops down to the next instruction. So here it is dropping down to the next instruction. It's the current instruction plus 4. So once again, these are all my branch instructions. I cut this out of one of the manuals here. You can actually, if you look at the manual, the pseudo instructions are darker, which didn't really come out on this. Not a big deal. So these are the 2 programs together. No sense in going over that anymore. But what I do want to show you is you have to understand the mechanics of these jumps and branches. And so essentially in the high level, there's two ways of going somewhere. I think of it as going to my neighbor's house. Do I go 2 houses down, or do I go to, I don't know, 372 Woodland Drive in Los Osos? Okay, the issue is I have 2 ways of getting there. One is an absolute address, and one is a relative address. So there's you need to understand both of these. This relative addresses means it says like go back 2 instructions, as this is associated with an absolute address, which means go to the instruction at this address in memory. And so 2 different ways to get to the same place. The hardware works with both, and you need to work that. You need to understand that. And the issue is, as a programmer, heck, you don't need to understand it. Poor programmers, they don't understand the hardware. I feel sorry for them. Okay, so once again, this is just this. Well, we'll look at this instruction. It's a jump and link. The idea here is it's jumping somewhere, and it's actually going to load a register with a value. So this is the one I told you should use, but this instruction, it actually does 2 things here. This is the jump part of it. I shouldn't have circled that. That's the jump part of it. It's taking the program counter and adding an offset to it. So the offset is some relative address. It's going to take that relative address and create an absolute address from it. Okay, and this part right here is it's taking the current address plus 4, current address in the PC plus 4, which is the address of the next instruction, and it is storing it somewhere. Okay, so we don't need to worry about that right now. That's associated with subroutine calls. We'll get into that later. So technically speaking, we're just looking at the unconditional branches for today. Subroutines is a topic for later. So this is the code associated with the JAL instruction, jump and link. Okay, so this is the format of a J-type instruction. JAL is a J-type instruction. Here it is. This is the actual the bit code for a JAL instruction. So what we have here is the opcode, and then we have 2 different field codes. Okay, so associated with this is this register right here. So we have 5 bits for a register value. So don't really need to work with that today, but what we're interested in is this this immediate value. So IMM stands for immediate value, and what this value is a relative. It's a number essentially that's used as a relative address, not an absolute address, but a relative address. So the hardware is going to take this relative address and create an absolute address from it, which I think we'll get into that in the next slide. But what I want to point out to you in this thing is there's the bits are out of order. Not a big deal. It's really easy to fix up in hardware, which you have to do later. But what is interesting here is that it does not, if you look at this thing, it does not encode the 0 value of the relative address. So the LSB of the address is not encoded. Okay, so that's kind of like, wow, what's the reason behind that? And so the issue is that the assembler, because it's instruction memory and instructions are 4 bytes long, it technically doesn't need, it's always jumping by 4, right? Well, so it doesn't need to encode the relative, or the 2 least significant bits, actually. It doesn't really need to encode the 2 least significant bits, but it does encode the second to least significant bit. So the only bit it doesn't encode is the least significant bit. And the reason it doesn't do that is because there's actually a form of RISC-V that has instructions that are 16 bits long, and we're not using that. So we're only we're using 32-bit instructions. We're only not encoding the LSB, and the reason is, wow, why what's the advantage of not encoding the LSB? And the advantage is the fact that this relative address is encoded as part of the instruction. So effectively, if I don't encode the LSB, I can jump further with the 20 bits that I actually do encode. So this is something that we'll get into in more depth later, but important that you understand that I'm working with relative addresses and absolute addresses. I'm creating an absolute address from the relative addresses, and since I'm jumping by 4 every time, I don't lose anything by not encoding the LSB.